Before we get into this, I need you to understand something. Scientists have been staring at one specific crater on Mars for decades, not because it's beautiful, not because it's the biggest, because something might have lived there. And right now, a six-wheeled robot the size of a family car is crawling across that crater floor, drilling into rocks that are older than life on Earth. Looking for proof. Stay with me, because what it already found is going to change the way you think about this solar system, and maybe about life itself. February 18th, 2021. The entire world was watching a live stream feed. A spacecraft was hurtling toward Mars at 19,000 kilometers per hour. No pilot, no manual controls, no abort button that would actually help. Just physics, mathematics, and years of human engineering being tested in real time for the very first time. The entry sequence had already begun, and there was absolutely nothing anyone on Earth could do about it. Here's the part that makes this even more surreal. The signal from Mars takes about 11 minutes to reach us. 11 minutes traveling at the speed of light. By the time Mission Control received confirmation that entry had started, the landing was already over. Had been over for 11 whole minutes. It had either worked or it hadn't. And the people in that room, the engineers and scientists who had spent years building this thing, sat there watching a screen, knowing the fate of their life's work had already been decided. They just didn't know the result yet. That's what space exploration actually feels like from the inside. Not the clean, confident drama you see in movies, but waiting. Helpless, nail-biting, stomach-dropping waiting. While a machine you built and launched and trusted does its job 480 million kilometers away, completely alone. Here's the thing about landing on Mars. People think it's like landing on the moon. It really isn't. The moon has no atmosphere whatsoever. You fire your engines and descend gently, straightforward, slow, controlled. Mars is different. Mars has just enough atmosphere to be a problem, but not nearly enough to be a solution. Too thin for a parachute to do the job on its own, too thick to simply ignore. The spacecraft hits that thin layer of air at hypersonic speed, and what follows is what NASA engineers call the 7 minutes of terror. 7 minutes. That's how long it takes to go from 19,000 kilometers per hour to a complete, gentle stop on the surface. In that window, a sequence of events has to unfold in perfect order. A heat shield protects the capsule from temperatures exceeding 1,300 degrees Celsius. A parachute the size of a house deploys at supersonic speed. The heat shield drops away. Radar scans the terrain below to find a safe landing zone. A rocket-powered sky crane, essentially a jetpack attached to a crane, lowers the rover on cables to the surface. The cables release. The sky crane flies away and crashes at a safe distance. And somehow, after all of that, the rover is sitting gently on Mars. 7 minutes. And engineers can't intervene once it starts. Every single decision, every if this then that, had to be programmed in advance. The machine had to think for itself. And it did. When the footage came back, actual high-definition video of the parachute deploying, actual color cameras showing the ground rushing up, people didn't just cheer. They cried. Because this wasn't just a machine landing on a rock. This was the opening act of humanity's most ambitious scientific mission. A question 3.5 billion years in the making. Are we alone in this solar system? Let's talk about where Perseverance landed. Because this wasn't random at all. Scientists spent our years debating the exact location. Hundreds of candidate sites were analyzed, narrowed down, argued over, studied from orbit. They needed flat terrain for a safe landing, but they also needed ground that was scientifically rich. Those two requirements almost never overlap. What they found was Jezero Crater, roughly 45 kilometers wide, located just north of Mars's equator, where temperatures are slightly more forgiving, and at least 3.5 billion years old. Let that actually sink in for a second. 3.5 billion years. When Jezero Crater formed, Earth was still in the middle of its own early experiments with single-celled life. Complex animals didn't exist yet. Neither did plants, neither did anything with eyes. And Jezero, even back then, already had liquid water in it. Real water. A real lake. Fed by real rivers flowing in from the surrounding terrain. Here's where it gets genuinely interesting. Ancient satellite imagery revealed something remarkable in the geology of Jezero's rim. The crater wasn't just a hole in the ground filled with old rock. It had river delta formations, fan-shaped deposits of sediment, exactly the kind created when a river slows down as it enters a standing body of water. You know what river deltas mean on Earth? Water flowed there consistently for millions of years. And wherever water flows on Earth, life follows, always, without exception. Every river delta, every ancient lake bed we find on our planet eventually reveals evidence of biological activity. The sediment layers in those ancient delta formations are like the pages of a history book. Each layer tells a different story. Each layer holds potential clues from a completely different geological era. Some of those layers are 3.5 billion years old, from a period when Mars may have had a thick atmosphere, substantial liquid water, and surface temperatures warm enough to sustain microbial life. A time when Mars wasn't the frozen, radiation-blasted, bone-dry desert we see today. A time when it was in some ways almost Earth-like. And during that time, something tiny, something microscopic, might have found a way to survive, to replicate, to grow, to leave traces. That is what Perseverance was built to find, not little green men, not alien spacecraft, not signals from another civilization. Bacteria. Ancient, fossilized, long-dead bacteria. Traces so small they might be invisible to the naked eye. Chemical signatures locked into rock that no geological process could create on its own. This is why the mission is so difficult to communicate to the public. There won't be a dramatic reveal. No alien skeleton, no crashed spacecraft, just a rock. A rock with chemistry that shouldn't be there. And that chemistry, if they find it, will be the most important discovery in the history of science. The rocks surrounding Jezero crater aren't just random rubble scattered across the surface. They represent a geological record spanning billions of years. Scientists identified something crucial before Perseverance ever left Earth. The outcroppings near the crater contained samples from multiple distinct geological eras, all within reasonable driving distance of a safe landing zone. No deep drilling required. No need to excavate hundreds of meters underground to find ancient material. The history of Jezero was exposed right there on the surface, carved open by ancient impacts, shaped by billions of years of erosion, waiting to be read. Think of it like finding an open-air library, all the books still on the shelves, billions of years of planetary history, just sitting there in the rocks. And Perseverance arrived with the tools to read every single volume. The rover carries a suite of instruments that would genuinely impress most Earth-based laboratories, cameras capable of resolving features at millimeter scale, a ground-penetrating radar system called RIMFAX, able to map what lies beneath the surface without touching it, multiple spectrometers that analyze rock and soil chemistry remotely, an ultraviolet laser that can identify organic molecules, and, most critically, a coring drill designed specifically to extract perfect cylindrical rock samples from the Martian surface. Samples sealed inside titanium tubes that could eventually make the journey back to Earth. That last part is the entire point. The goal isn't just to look for life on Mars from a distance. The goal is to bring pieces of Mars home, to hand over actual Martian rock to the best scientific laboratories on Earth. Because if life existed there, the evidence might be so subtle, so chemically complex, that no robot can definitively confirm it alone. We need human analysis, Earth-based instruments, years of careful study. Perseverance is the beginning of that chain, the most important first step. And it all started with a crater that has been dry for 3 billion years, but wasn't always. There's something else worth understanding about Jezero, something that makes scientists genuinely excited when they talk about it. The crater isn't just an ancient lake. It's a preserved snapshot of an era when Mars was a fundamentally different planet. Think about what that means. When water flowed into Jezero through those ancient river channels, it carried sediment, sand, silt, clay particles, organic material, if any existed. All of it slowly sank to the bottom of the lake, layer by layer by layer. Like rings in a tree, those layers recorded changing conditions over millions of years. Changes in temperature, changes in chemistry, changes in the atmosphere above. And here's the part that makes geologists almost giddy: clay minerals. Orbital spectrometers spotted clay mineral signatures in Jezero before Perseverance ever landed. Why does that matter? Because clay minerals only form in the presence of liquid water. They don't appear by accident. They are direct chemical evidence that water was there, not just briefly, not just in a flash flood, persistently, over long timescales, long enough for minerals to fully transform. On Earth, clay-rich lake sediments are some of the most productive places to search for fossilized microorganisms. The clay itself acts as a preservative. It traps biological molecules, it locks them in. It protects them from degradation for geological timescales. Scientists have found 3-billion-year-old microbial fossils preserved in Earth's clay deposits. 3 billion years. Still readable, still identifiable. If Mars had even a fraction of that biological productivity, and if those clay sediments in Jezero did the same job they do on Earth, then the rocks Perseverance is drilling could contain the molecular fingerprints of life, preserved across the entire age of the solar system. Waiting, that's not wishful thinking. That's geology. That's chemistry. That's why Jezero Crater was chosen above every other location on the planet. Here's the part nobody really talks about. After one of the most spectacular landings in the history of space exploration, Perseverance just sat there. For months. Almost 5 months. You'd think a robot sent 480 million kilometers to search for signs of alien life would immediately start searching. Get moving. Explore. Drill. Make history. But science doesn't work that way. And it turns out, Perseverance had a very good reason to wait. Because it wasn't alone on that landing day. And what it had secretly brought with it was about to make history in a completely different and completely unexpected way. Tucked underneath Perseverance's belly, held in place by a carbon fiber wind guard, was a passenger. Small, fragile-looking to the untrained eye. Barely 1.8 kilograms. 4 spindly landing legs. 2 counter-rotating rotor blades. 1 small camera. Its name was Ingenuity, and it was about to attempt something that had never been done anywhere other than Earth. Powered, controlled flight on another planet. Let that fact sit for a moment. The Wright brothers achieved the first powered flight at Kitty Hawk, North Carolina in 1903. Barely 12 seconds, barely 37 meters, barely off the ground. But it was the first time humans had flown under their own mechanical power. And just 118 years later, an eye blink in the history of aviation, a helicopter was hovering autonomously above the surface of Mars. That gap is almost impossible to fully process. From a wooden biplane struggling to stay airborne for 12 seconds, to a robotic drone flying a self-planned route on a different world, in just over a century. But first, Ingenuity had to survive long enough to fly. And Mars is not a gentle environment for small, delicate machines. The Martian atmosphere is roughly 100 times thinner than Earth's. 100. On Earth, helicopter rotors push against dense, thick air to generate lift. The air pushes back. That resistance is what makes flight possible. On Mars, that same air is essentially nothing. A rotor spinning at normal helicopter speeds would just cut through near vacuum. No lift, no hover, no flight. Just a very sophisticated and very expensive paperweight spinning in the Martian breeze. The engineers who designed Ingenuity understood this from day one. So they built something unlike any helicopter that had ever existed. Ingenuity's rotors spin at over 2,700 revolutions per minute. For context, most full-sized Earth helicopters operate at roughly 300 to 500 RPM under normal conditions. Ingenuity's rotors had to spin 5 to 9 times faster just to compensate for the thin air. And the entire machine had to be reduced to its absolute minimum weight. Every component was stripped down. Every gram was interrogated. The result was a machine that looked almost too fragile to fly anywhere. The fact that it flew on Mars makes it one of the most elegant engineering achievements in human history. March 21st, 2021. The preparation began slowly. Perseverance carefully backed away from its landing site and drove to a flat, clear patch of Martian ground designated as the helicopter's airfield. The area was about the size of a boxing ring. Smooth enough, clear enough, perfect. The first step was removing Ingenuity's protective wind guard. Millimeter by millimeter, the shield was pulled back. For For the first time, Ingenuity felt actual Martian air against its rotors. Cold, impossibly thin, utterly alien. The scientists watching from Earth monitored every sensor reading before authorizing the next step. No rushing, no shortcuts. This was too important to hurry. The process took days, slow, careful days of incremental progress and constant data verification. April 3rd. Ingenuity's 4 legs touched Martian soil for the very first time. It was on its own. Then came the first real test. Not a flight, not even a rotor spin. Just a night. One Martian night. Temperatures on Mars dropped to -100 degrees Celsius after sunset. Without the warmth of Perseverance's internal systems to protect it, Ingenuity was completely exposed. Its own heaters, running off a small battery charged by solar panels, were the only thing standing between the helicopter's delicate electronics and total destruction. If those heaters failed, the components would freeze. The battery would discharge to nothing. The flight mission would be over before it ever began. Dawn arrived. Data from Ingenuity streamed toward Earth. 11 minutes of travel time. Then the signal arrived. Every system nominal. Battery charged, temperature holding. Ingenuity had survived its first Martian night. The scientists exhaled. April 19, 2021. A date that will eventually appear in history textbooks. Ingenuity's rotors began to spin. Slowly at first. Then faster, faster. Until they were a blur moving so quickly the human eye couldn't track individual blades. 2,537 revolutions per minute. Perseverance stood nearby at a safe distance, its cameras locked on the small helicopter, watching, recording, waiting, and then, quietly, impossibly, beautifully, Ingenuity lifted off the surface of Mars. 3 meters in the air, hovering perfectly steady, not drifting, not wobbling, just hanging there in that thin Martian air, like it had always belonged in the sky. 39.1 seconds. Then a smooth, controlled descent back to the ground. On Earth, the team who had worked on this technology for 6 years completely lost their composure. Tears, embraces, shouting, laughter, because they had done something that seemed genuinely impossible when the project first began. Powered flight on another world, the first in human history. And nobody would ever be able to take that away. What came next surprised everyone. Ingenuity didn't stop. What was planned as a brief technical demonstration, 5 flights maximum, maybe 30 Martian days total, turned into something far more valuable. The helicopter kept flying. It flew higher, faster, across greater distances. It scouted terrain that Perseverance couldn't safely cross. It photographed rock formations from angles no ground-based rover could ever achieve. It identified the best routes forward, saving the rover weeks of potentially dangerous guesswork. Ingenuity transformed completely. From a disposable demonstration piece at the start of the mission into a full active partner in the search for ancient Martian life. A scout, an explorer, an aerial pioneer on another planet. A breakthrough that nobody had anticipated when it was approved as a last-minute addition to the mission. While all of this was happening, Perseverance was far from idle. The big rover, yes, it took a few selfies and they're honestly outstanding, was working through its own checklist, testing every system, checking every instrument, preparing for the journey ahead. And in the process, it gave the world something genuinely moving. Sound? The rover's microphone, the first ever sent to the surface of Mars, captured audio of Martian wind, real sound from the surface of another planet. When those recordings reached Earth, people listened in silence. The wind on Mars is faint, thin, almost ghostly. But it's there, a whisper moving across a cold, silent landscape 480 million kilometers from the nearest human ear. It makes Mars feel less like a picture on a screen, more like a place, a real place, with weather and atmosphere and sound. Just not one built for us. Perseverance also conducted dozens of short test drives across the crater floor, checked its mobility systems on different terrain types, tested its robotic arm, calibrated its drill, ran diagnostics across every scientific instrument on board. Because when the real mission began, there would be no going back for repairs, No spare parts store, no rescue mission. If anything broke out there on the Martian surface, that was the end of it. Everything had to work perfectly from the start. And there were moments during those months where that pressure became visible. The first rotor spin test on Ingenuity hit a software glitch. Not catastrophic, not mission-ending, but a reminder that nothing in space exploration is ever as simple as it looks. Engineers stayed late, rewrote code, reran simulations. They fixed it. That's what this team does. Perseverance also had its own anxious moments. During one early arm deployment test, a sensor reading came back slightly outside nominal range. The whole team paused, analyzed, debated, determined it was within acceptable parameters, continued. But every anomaly is treated as a potential mission ender until proven otherwise, because on Mars, you don't get a second chance. The psychological weight of operating a billion-dollar machine on another planet is hard to overstate. Every decision echoes. A wrong turn into a sand trap, a drill bit that breaks on a particularly hard rock, a software update that doesn't install correctly. Any single thing can end everything, and yet the team kept moving, kept testing, kept preparing. Not because they weren't afraid of failure, but because the question they were trying to answer was worth the risk. Was worth every sleepless night, was worth every rechecked calculation and every triple-verified sensor reading. Because the alternative, not asking, wasn't acceptable. Not anymore. Not with a rover sitting right there in exactly the right place, with exactly the right tools. Arguably the most quietly revolutionary thing Perseverance did during those early months. Something that barely made the headlines, but something that might matter more than anything else for the future of humanity beyond Earth. Here's where it gets strange and wonderful and a little hard to believe. Keep watching. Here's something that should have been front-page news, buried in the list of Perseverance's early achievements. After the landing footage, after the helicopter, after the audio, was a small experiment. An experiment about the size of a car battery. That quietly changed the future of human spaceflight. It made oxygen. On Mars. From the Martian atmosphere itself. And if you think that sounds like science fiction, let me explain why it's the most practical thing humanity has ever done on another planet. Carbon dioxide makes up about 95% of the Martian atmosphere. CO2, the molecule we breathe out, the waste product of animal metabolism. On Mars, that waste is everywhere. It fills the entire sky. It howls in Martian windstorms. It freezes into dry ice at the poles. It is, for all practical purposes, the atmosphere of Mars. And inside that molecule, bonded to a single carbon atom, are two oxygen atoms. Two. Sitting right there. Waiting. MOXIE, which stands for Mars Oxygen In Situ Resource Utilization Experiment, was designed to break that bond. To separate the oxygen from the carbon using a process called solid oxide electrolysis. To take a molecule the human body cannot use and transform it into something essential for life. In its first test on the Martian surface, MOXIE produced approximately 10 grams of pure oxygen in 1 hour. 10 grams. You could hold it in your hand. It's not much in absolute terms, barely enough for a person to breathe for a few minutes. But that is spectacularly not the point. MOXIE is a prototype, a proof of concept. Its purpose wasn't to supply oxygen to anyone. Its purpose was to demonstrate, in actual Martian conditions, with actual Martian air, at actual Martian temperatures, that this chemistry works, that the technology functions, that it doesn't fail when exposed to the brutal reality of the Martian environment. And it worked. Scale that technology up 100 times, which engineers consider technically feasible with current knowledge, and suddenly you have a machine capable of producing enough oxygen to keep humans alive on Mars indefinitely. Not theoretically, not in a simulation, actually. A machine running off solar power, breathing in Martian air, breathing out the gas that sustains human life. But breathing is only half the story. Here's where the numbers become truly staggering. Oxygen isn't just for lungs. Oxygen is rocket fuel. To launch a rocket off the surface of Mars, to achieve Martian escape velocity and head back toward Earth, you need enormous quantities of propellant, Current estimates put the requirement at 30 to 45 metric tons of propellant per launch, depending on the payload and trajectory. 30 to 45 metric tons. That is not a small number. Under the current plan, all of that fuel would need to be brought from Earth, launched first, then shipped across hundreds of millions of kilometers of interplanetary space, accounting for a significant fraction of the mission's total mass, and therefore a significant fraction of its total cost. It makes Mars missions almost prohibitively expensive. It's one of the primary engineering barriers to actually putting humans on Mars and bringing them home again. But what if you didn't need to bring the fuel? What if you could manufacture it on Mars, using resources that are already there? Liquid oxygen, produced by a scaled-up MOXIE system, is a primary oxidizer in rocket propellant. Combine it with liquid hydrogen, which can theoretically be extracted from subsurface ice deposits on Mars, and you have a complete functional rocket fuel made on Mars from Martian resources. No cargo missions from Earth carrying tons of propellant. Just a machine working in the background, filling a tank day after day, preparing for a launch that might still be years away. MOXIE proved this is not a fantasy. A small box installed in a rover on the surface of another planet made actual oxygen from actual Martian air. And that single quiet experiment may be the key that eventually makes human civilization on Mars not just possible, but economically viable. Most people missed it entirely. The helicopter was flying, which, to be fair, was spectacular. June 1st, 2021, exactly 4 months and 12 days after landing. The wheels of Perseverance began to turn in earnest. Not a test drive, not a short systems check, the actual mission, the beginning of the search. The route debate had been settled. Scientists chose the longer clockwise path around the sand dune field, more travel time, but far more scientific value along the way. More rock formations, more sample opportunities, more data. Because every rock is a potential page in that 3.5 billion year story, and they wanted to read as many pages as possible. The rover rolled out slowly, its 6 aluminum wheels pressing into the ancient Martian sediment, leaving tracks that will almost certainly remain visible for centuries, possibly millennia. Because on Mars, with no rainfall and almost no erosion at human-relevant timescales, marks persist. Those wheel tracks are a record. Physical proof that something from Earth came here and moved with deliberate scientific purpose. The rock samples Perseverance began collecting weren't randomly chosen. Each sample site was identified through a layered process of orbital spectral analysis, surface camera surveys, and scientific prioritization. Teams of geologists on Earth reviewed every candidate location, argued over which formations were most likely to contain biosignatures, debated the chemistry, the age, the exposure history. Only then was a drilling site approved. And the drill, the most critical piece of hardware on the entire mission, had never actually been tested in real Martian conditions until that moment. Every test had been conducted on Earth, under simulated Martian temperatures, under simulated low atmospheric pressure. But simulations are always approximations. The real thing is always different. The drill worked. It extracted clean, cylindrical core samples from ancient Martian rock. Millimeter-perfect plugs of geological history, each one sealed inside a titanium tube approximately the size of a thick pen, each one labeled and stored with extraordinary care, each one representing a potential answer to a question that humanity has been asking for thousands of years. These tubes are not staying on Mars permanently. The mission includes a future retrieval phase, a separate spacecraft yet to be launched, that will land near Perseverance's sample depots, collect the tubes, and carry them back to Earth, where laboratories the size of buildings can analyze them, where mass spectrometers capable of detecting a single organic molecule can search every sample, where the sharpest scientific minds on Earth can look, really look, for the chemical fingerprints of ancient life. If there's a fossil record on Mars, it's inside those rocks. Because Jezero Crater is exactly the kind of environment where ancient microbial life would have lived, thrived, died, and left traces. A warm lake, a river delta, millions of years of sediment accumulation, conditions almost identical to the early Earth environments where the first single-celled organisms appeared. almost identical. Here's where the story gets genuinely unsettling, in the best possible way. Mars and Earth have been exchanging material for billions of years. When asteroids impact Mars at high velocity, they blast fragments of Martian rock into space. Some of those fragments, traveling slowly through the inner solar system, eventually drift toward Earth. Some of them survive atmospheric entry. Some of them land in deserts and polar ice fields and are eventually found. We know this because we have them. Martian meteorites sitting in Earth's museums, identified by their unique chemical signatures. Pieces of Mars that made the journey here entirely on their own. Now hold that thought. If life existed on Mars 3-5 billion years ago, when both planets had liquid water, warm temperatures and the essential chemistry of biology, is it possible that life didn't evolve separately on each world? Is it possible that the first living organisms on Earth arrived from Mars? That we are, in some deep and uncomfortable sense, Martians? Or that life on Earth and life on Mars share a common ancestor, launched into space by an ancient impact, surviving the long cold journey, landing, adapting, spreading? That hypothesis, called panspermia, was considered fringe science for most of modern history. Today, mainstream astrobiologists take it seriously. The evidence isn't there yet, but the mechanism is plausible, and the chemistry is compatible. And if Perseverance finds definitive evidence of ancient microbial life in Jezero crater, that question doesn't just become more interesting. It becomes the most urgent scientific investigation in human history. Because if Mars had life, and Earth has life, and rocks travel between them, the implications are almost too large to hold in your head at once. Perseverance is still out there, rolling, drilling, collecting. Ingenuity still flies when conditions allow. Scientists on Earth analyze every image, every spectrometer reading, every soil sample. Future missions are in development. The sample retrieval mission is being designed. A chain of exploration stretching across decades is already in motion. And it all began with a 6-wheeled robot surviving 7 minutes of pure terror and setting down gently in an ancient, dried-up lakebed on a world that was once, maybe, alive. Every wheel rotation is a question pressed into ancient soil. Every rock sample is a potential answer sealed in titanium. Every kilometer driven is another chapter in a story that started 3.5 billion years before the first human being existed. Somewhere in those sealed tubes, waiting quietly for the long journey home, might be the most important discovery our species has ever made. We just don't know it yet. The rover is still looking. So here's the question I'll leave you with. If Perseverance returns evidence of ancient microbial life on Mars, what does that actually mean? It means life isn't rare. It means that given the right conditions, life happens, reliably. It means the universe is probably full of it. And it means every star you can see on a clear night, each one with its own family of planets, suddenly becomes a question worth asking. Is that terrifying, exciting, both? Drop it in the comments. If Mars had life on even just bacteria, even just traces, does that change how you see our place in this universe? Because it should. And the rover is still out there right now, still rolling across that crater floor, still drilling into 3-billion-year-old rock, still asking the question on behalf of every human being who has ever looked up at a red dot in the night sky and wondered,